All right, so let's talk about now what happens if we launch them at an angle. Well, if we launch them at an angle, they're still going to fall. They're still going to fall according to gravity, and it's always going to be off by, or it's always going to be 5 times t squared below where it would be if there weren't any gravity. Now let me explain how they get this. And by the way, this 5, once again, it's a round off from the 10, but this comes from this formula. Distance equals 1/2 at squared. And so what we're saying is that if a, instead of a, let's call it g, is 10, well, 1/2 times 10 is 5. So we're saying that the distance that it falls is 5 times the time squared. So in other words, after 1 second of our object that I've thrown that would go in that path, after 1 second, it will be 5 feet below the line where it should be. After 2 seconds, it will be 20 feet below the line. So here's my second. So that's where we get that curved path. No matter what angle we throw it at, it's always going to be that same distance below the line. Okay, so here we go. So here's my my first example. We throw this out perfectly straight. We threw it out straight. In 1 second, it's going to be 5 feet below. 2 seconds, it's going to be 20. 3 seconds, it's going to be 45. And it's going to do that no matter whether I threw it straight or whether I threw it at an angle. Now, this is my point where it would be if there were no gravity. But it is now 5 feet below, or 5 meters below that. Here it's 20, and here it's 45. And if I even threw it down, it's the same thing. It's going to be 5 meters below where it should be. It's going to be 20 meters below where it should be. It's going to be 45 meters below where it should be. That's how that works, no matter what. Okay, it's always the same. All right, so that's pretty much telling you the same thing that I talked about there. All right, so let's take a look at this projectile. This cannon fires at this angle. So no gravity, that's where it goes off the screen. But because of gravity, after 1 second, it has fallen 5 meters. After 2 seconds, it will have fallen 20 meters. And after 3 seconds, it will have fallen 45 meters off of the original path of what it was going to be on. Just like that. Like that. And here's that formula that I talked about. This is how they get this. Distance equals 1/2 gt squared. Technically, you know, once again, this should be, instead of 5t squared, really, you know, 4.9 t squared if you want to be a little more exact. But that's how they get that formula. All right, so for the height, for the component vectors of the cannonball's motion, the horizontal component is always the same. The only thing that changes on this is the vertical. So the horizontal stays the same. Vertical is going to be 5 feet lower, or 5 meters lower after 1, 20 after 2, and so on. That's the only difference. Okay. Now let's take a look at this example here. If we launch this projectile at an angle, and notice that at the beginning, I've got my component broken down into horizontal and vertical components. Notice what happens down the road. Notice that this component has gotten a lot smaller. That's because there was acceleration due to gravity. But notice that this component is exactly the same. But my overall arrow here is a lot smaller than what it was here. Well, think about it. As we're getting up to the top, this object is slowing down, right? And eventually it's going to come back and then start to accelerate as we go back. Okay, so at this point at the top, it's got no vertical component of velocity at all. It's stopped. And then it starts to go down again. And then it starts to go down even faster. So when it hits, notice that this component here is now just as big as this one was here. So this object, and once again, air resistance is neglected. Once again, if this object just, if this had this acceleration upward, whatever it had upward, that's how fast it's going to hit the ground when it comes down. So if you fired a rifle straight up, when that bullet comes back down to hit the ground, it's going to be going just as fast as it did when it left the gun. And it's going to be just as deadly when it hits the ground. That is, of course, if we don't take into account air resistance. And there's going to be, if you took into account air resistance, there's considerable difference in the speed. However, still fast enough to kill you. Let's talk about range, because the angle that you shoot something makes a big difference as to how far something goes. Take a look at these two graphs. Notice how in the second one we shoot it straight or higher up, and it doesn't go quite as far. It doesn't have this same range that we had over here. I mean, think Angry Birds, okay? If you're playing Angry Birds and you've got to get something right in here, you don't want to pull it back at this angle. It's going to overshoot it. It's going to miss this object right here. So you give it a little higher angle, or maybe you point it down more, whatever. But you don't shoot it at that same angle, if you want to get to it. So frustrating. All right, so let's take a look at how these horizontal ranges differ based on angles. And take a look at this and notice that depending on what angle you kick it at, how far it's going to go. So obviously if we want to get the goal, if our job is to get the goal here with whatever speed he's kicking it at, we want to follow this path. The 60-degree one or the 30-degree one. Notice that they both end up in the same place. Or let's go to here, look at 75. If you go 75, notice that that ends up at the same as 15. Well, what you'll find is that angles that add together to give you 90, so 75, 15, 75, they end up in the same place. Angles that add, here 30 and 60 ends up in the same place. So angles that add up to be 90 end up giving you the same answer of where they're going to be. So complementary angles. Now the maximum range, if you notice that the maximum range that you're going to get, like in that soccer example, the maximum is 45 degrees. So the perfect angle to shoot something at to get the maximum range is 45. It's when your horizontal component and your vertical component are the same. The problem is if you shoot it up too high, your horizontal component isn't enough. And if you shoot it out farther, your horizontal component is more, but it doesn't get up high enough to stay in the air long enough to go far. Okay. So without air resistance, we're going to get the projectile will reach maximum height in the same time it takes to fall. So a lot of times, one thing to keep in mind, anytime we have to figure out problems and you start at the bottom and you got to go up and you got to come back down, a lot of times you can just say, hey, well, start at the top and drop it or finish it from there. Because the time it takes to go from here to here is the same as the time to go from here to here. Assuming, of course, no air resistance and all that good stuff. And so we can figure that out. So a lot of times that's very helpful when we're trying to figure out problems on here. So here's my example. We shoot this cannonball. It leaves the cannon at 50 meters per second. Then goes 30, 10. Notice that right there at the same one, they're both 10. Up here it would be 0. Right here they're both 30, and by the time it comes back down, it's back to 50 again. And if somehow it could go below the ground, if this was a cliff and it went off the cliff, then it would go faster. But at that point, it's always the same on each area as you go up and down. Notice what happens if we do have air resistance. So here we're talking about air resistance. This is my perfect angle. This is my parabola. That's where it should go. But, oh, air resistance messes me up. I lose a lot of my horizontal component, and I'm going to fall down a lot shorter than that. So in real life, we don't get that. Now, things like a cannonball, they're not as affected by air resistance as other things, but they still do have that effect. All right, so here's a good question. The longest time a jumper is airborne for a standing jump, or hang time, is 1 second. For a record 1.25 meters, or 4 feet. Can anyone in your school jump that high, raising their center of gravity 1.25 meters above the ground? Reagan, how about you? Think about that. So they're talking about somebody standing on the ground and jumping. You know, like somebody stands under a basket and goes up to dunk it, just standing, not running and jumping, but just standing and jumping. The maximum time that they're in the air is 1 second. That's it. And that gives them 4 feet off the ground. Now that's quite a ways. That's a pretty good vertical jump. You know, it's a 48-inch vertical jump, and I don't think we have anybody who can come anywhere close to that. And that's only 1 second in the air. So you are not in the air very long when you jump. All right, think about this. The projectile is launched at an angle into the air. Neglecting air resistance, what is its vertical acceleration? It's horizontal acceleration. Now, don't tell me you can't figure it out. There's not enough information, because there is. You can tell me both of these easily. Well, its vertical acceleration is 10 meters per second squared, because that's gravity. Horizontal is 0, because you've let go of it. There's no more horizontal acceleration. At what point in its path does a projectile have minimum speed? Where would have the minimum? Well, the minimum speed is at the top. That's where it would no longer have horizontal, or no longer have vertical component to it. It would only have its horizontal speed. If you're going straight up, it would be stopped. If you were throwing it out, it would just have the horizontal component of it. All right, just some questions here. I'm going to click through these. If you want to answer them, stop the video after each one and take a look. All right, hope you enjoyed the show.